Math 1314, Tyler Junior College, Section 4.4, Exponential and Logarithmic Equations. Logarithmic equations, all logs. In the previous video, we talked about logarithmic equations in which some terms were logarithms and some terms were not. By contrast, these equations have all logs. This term is a log, this term is a log, this term, and this term are all logs. Now, does that change our approach? Hardly, just a little bit. You'll notice over here I have the 4 steps from last time, all condensed down to one word each. Condense into one logarithm, rewrite in exponential form, solve the remaining equation, check for extraneous solutions. Our plan of attack on these is almost identical except one of them moves. So let's start with the first equation. Solve log base 3 of 17x plus 1 equals log base 3 of 5x plus 37. Well, there's no need to condense, although we have 2 logarithms, there's just one on each side. When I say condense, I mean condense the left side or the right side, or both if necessary. Clearly, we'll have to do it over there. So we can skip step 1, there's no need to condense either side. So what do we do instead of rewrite? Well, we take advantage of the fact that logarithmic functions are 1-to-1. And without rehashing all that, that basically means that if the outputs of 2 logarithms are equal, that means the inputs had to be equal. In other words, if 2 logs with the same bases are equal, then their arguments have to be equal. So we're going to rewrite, we're going to change the second step from rewrite to cancel logs. Now, it is important to point out that you do not cancel logs until there is one on the left and one on the right, which is exactly what we have on this first example. On the second, if you just went, I'm going to cancel all the logs, you would get 0 credit for this problem from every professor because you did nothing correct and totally missed the point on how to begin it. So you can only cancel logs when it is a log on the left and a log on the right. If you want a more specific step, you could say rewrite log base b of m equals log base b of n as m equals n, to emphasize that there must be one log on both sides. Now, if you've done the condensed move, you have one log on both sides. So don't cancel logs until you have one log equal to one log, and they have to have the same base. If they don't have the same base, it's an interesting exercise, a little beyond what we discussed in this course. I can make an optional video over it, but right now it's kind of late in the day and I'm hungry. All right, let's cancel the logs. 17x plus 1 equals 5x plus 37. Oh, now I just have to solve and check for extraneous solutions. Too many x's, subtract the smaller one. And I always like subtracting the smaller x because it leaves the other one positive. 12x plus 1 equals 37. You should be able to solve this in your head. I'm going to write the steps. Subtract 1 from both sides, you get 12x equals 36. Then divide both sides by 12. But before you stick a fork in it or put a box around it, better make sure it's not extraneous. And that basically boils down to, when I substitute it back in, will it cause any of the arguments to be negative or 0? And a real quick look will go, no it won't. 17 times 3 is positive, add 1 and it's still positive, that's all I really need to check. 5 times 3 is positive, add 37, it's still positive. So it's not extraneous in the sense that it showed up and it never was supposed to be a solution. If you really want to make sure it's a solution, make sure the arguments end up being the same. 17 times 3 is 51, plus 1 is 52. 5 times 3 is 15, 15 plus 37 is also 52. So we're good. I'm not sure what happened there. But what about the other one? Well, it's nothing we can't handle. It's going to be a little bumpier of a ride, but I think we'll enjoy the ride. Solve 2 times natural log of x minus natural log of x plus 1 equals natural log of x plus 2. Do you remember what I said you shouldn't do first? Don't cancel the logs. Don't skip this first step. If you go, cancel all the logs, it's wrong. End of story, no credit. Don't cancel until you have one log on both sides. I've got one log on the right, it's the left I need to condense. But the condensing here isn't that hard. We've practiced that. I'm going to use the quotient rule because of the minus, but not yet because of the coefficient. Bring in the power rule. Power rule says if there's a coefficient, move it in as a power on the argument. I can rewrite the first log as a natural log of x squared minus a natural log of x plus 1 equals a natural log of x plus 2. But I'm not done condensing because I still have two logs on the left. Bring in the quotient rule that says if you have one log minus another with the same bases, natural log is base e, then you can condense it into a single log that's the ratio of the arguments. The positive log's argument goes on top, the negative log's argument goes on the bottom, and the left condenses into the natural log of x squared over x plus 1. In the meanwhile, the right side is like, hurry up and get your stuff together, left side. But at this point, we're done condensing, and we have one log on both sides. So now, and only now, can we cancel the logs. Now you can go, cancel the logs. Now that leaves us x squared over x plus 1 is equal to x plus 2. And we're not out of the woods yet, because now we have to solve that rational equation. A lot of algebra is, let me change it from one problem to another, and eventually you fix all the problems. Do you remember the best way out of solving this, or what a good first move is? Hint, what's better, an equation with a fraction or an equation without a fraction? Don't answer, it's obviously the second. If you're ever solving an equation with a fraction, it's in your best interest to multiply both sides by something that is capable of canceling all the denominators. And since the only denominator is x plus 1, that's what we're going to multiply both sides by. Yay, we're canceling. X squared equals x plus 2 times x plus 1. Oh, look, the right side's factored. Yay, but it's not equal to 0, so the factorization is completely useless. So we have to bust it open. Foil this out. You get x squared plus 2x plus 1x, which is plus 3x, plus 2. Oh, goody, now it's a quadratic equation. It's like we always fix one problem and get another. But that's okay. The problem's getting better. It used to have logs, it used to have fractions, now it has neither. And this looks like a quadratic equation. Guess what? It's not really. I know it has an x squared, but how do we solve quadratic equations? Get them equal to 0. Let's empty out the left side by subtracting x squared. But if we subtract x squared from both sides, oh, look at that. All the x's drop out. And now it collapses down to a little bitty linear equation, which I'm going to move up here. Easy solve. Subtract 2 from both sides. Divide both sides by 3. Easy peasy lemon, wait a second. Before you put a box around it, which I just did, we didn't do step 4. Check for extraneous solutions. You have to go back to the original equation before anything happened. So way up here, and see if this causes trouble. Does it cause trouble here? Negative 2/3 plus 2 is positive. Positive what? Don't know, don't care. I'm just checking to see if it makes a negative argument. So it's okay there. Negative 2/3 here is okay, because 2/3 is less than 1. So negative 2/3 plus 1 is going to be positive. But negative 2/3 here kills it. Because negative 2/3 stays negative. End of problem. You are not a solution. How did it get to sneak in? If you had gone to this line, it would have worked. Because it's good here, now it's good here because it got squared. Remember, anytime you condense, you're fiddling with the domains of the logarithms. So condensing will bring in more numbers that are valid now that weren't valid before, such as negative 2/3. Bad solution. You make this argument negative. We have no tolerance for negative arguments. Interpret that however you may. The only solution that could have been a solution was not a solution, which means there are no solutions. All that work just to say this? Yes. Why? Because. Well, number one, it's a good academic exercise. It makes stronger synapses in your brain. Excuse me. But number two, here's a real-world interpretation of what just happened. Let's say you're an engineer and you're trying to build something that meets certain specifications. Those specifications lead to certain equations on the dimensions of the thing that you're building. All right, I did the analysis and I assigned a dimension to how long a bridge needs to be, and I did the engineering and the physics and the math, and according to what you want me to build, whatever I need has to solve this equation. I know it came out negative, but let's ignore that for a second. All right, solve it and tell me how long to build this thing. I'm sorry, you can't build what you want. What you want is impossible. Why? Because the only thing that could have worked didn't. This equation has no solutions. Sorry, you have to give up on something. So there's a real-world interpretation to an equation having no solutions. If the equation is attempting to find a value to build something, measure something, or whatever something, and it has no solutions, that means that whatever you want is impossible. And I believe, let me double check, but I believe that that is the end of this section. It is. Don't get me wrong, there's some really nifty equations I'd love to do, but number one, this is video number 6. Number 2, it's probably pushing 5 o'clock. I don't know, I don't have a clock handy. And number 3, I'm hungry. All right. If you got any questions or comments, leave them in the video. Love to hear from you. Thank you.